Let's look at the first problem to find the zeros for this function. This is a quadratic function, and as I said before, if it's not obvious to you how to factor it, you should just go ahead and use the quadratic formula. So to use quadratic formula, the zeros equals to negative b plus or minus square root b squared minus 4ac over 2a. And in this case, b is 5, therefore negative b is negative 5 plus or minus underneath the square root 5 squared minus 4 times 2 times 8 divided by 2 times a is 2, so another 2. That equals to negative 5 plus or minus underneath the square root we have 25 minus 64 divided by 4. This equals to negative 5 plus or minus underneath the square root, that's negative 39, okay, over 4. Before we would say that this is undefined, but because now we have already learned about the complex numbers, we know that, as a side note, square root negative 39 equals to square root of 39 times square root of negative 1, and because we know that square root of negative 1 is I, so this is simply equals to square root of 39i. So we have negative 5 plus or minus square root of 39i over 4, and these are the two zeros, so x1 equals to negative 5 plus square root of 39i over 4, x2 equals to negative 5 minus square root of 39i over 4. So that's the answer to this problem. Next problem, to solve for inequality of this expression, this problem right here. On the left hand side we have this is the third degree polynomial expression, and we're going to use the graphical method to solve this inequality, which means that we're going to graph the left hand side, fx equals negative x to the third power plus 3x squared minus 2x, and this equals to pull out the negative sign first, x to the third power minus 3x squared plus 2x, and now we can pull out the x, which is the common factor, that equals to x squared minus 3x plus 2, and this should not be that difficult to factor. This equals to x minus 1 and then x minus 2. Now after this is completely factored, we can now graph the sketch for this function. We have the three zeros, they are all real, they correspond to the x-intercepts on your graph. The three zeros, or the three x-intercepts, are 0, 0 from the first one, positive 1, 0, and then positive 2, 0. Okay. Therefore, to sketch it, we know that the leading coefficient is negative, therefore the right tail goes down. The degree is 3, which is an odd number, therefore the left tail goes up. We know the three x-intercepts on the graph, 0, 0, 1, and 2. And based on this information, we can graph the function to be it doesn't have to be accurate. All we need is to be able to determine the regions that would make the function value smaller than 0, therefore smaller or equals to 0. Therefore we're looking for the region here. That's when the function value is below or equal to 0, and this region here. Therefore, based on our graph, we'll be able to solve this inequality, that x is either between 0 and 1, or x is bigger or equal to positive 2. And that's the solution to this problem. Next problem, for this polynomial function, this is a 4th degree polynomial function, and we have one given 0, and we need to find all zeros, and we need to write the polynomial as a product of linear factors. Now, this is a 4th degree polynomial function, which means that overall there should be 4 zeros. They could be complex, they could be repeated, but it will be exactly 4. Now, because we are given the first 0, this one right here is a complex 0, and we know that if a polynomial function has complex zeros, they would appear as conjugate pairs. Therefore, if x equals to 2 minus 3i is one of the zeros, the other one should be its conjugate, 2 plus 3i. Therefore, the first two factors are x minus 2 minus 3i, and another one is x minus 2 plus 3i. Okay, so this original function equals to these two multiplied by another unknown factors. So what we're going to do is we'll first find the product of these two factors, and then divide the original function by the product of these two factors, so that the answer will give us the product of these remaining two factors. To find the product of these two, we write them as x minus 2 plus 3i multiplied by x minus 2 minus 3i. And because we know that a plus bi multiplied by a minus bi simply equals to a squared plus b squared, because of that, this equals to x minus 2 squared plus 3 squared, which equals to x squared minus 4x plus 4 plus 9, which equals to x squared minus 4x plus 13. Next, we're going to use the original function divided by this product, and we're going to use long division. So we have x to the 4th power. Now, keep in mind that you need to count for all terms. In this case, you have a missing x to the 3rd power term. Therefore, you have to fill in a 0 to be the coefficient for this x to the 3rd power term. Therefore, we have x to the 4th power plus 0 x to the 3rd power minus 8x squared plus 72x minus 65 divided by x squared minus 4x plus 13. So we will have x squared here. Subtraction, 0 minus negative 4, positive 4. Negative 8 minus 13, negative 21. Write down the next term. The next one right here should be 4x. 16x squared plus 52x. Subtraction, negative 21 minus negative 16, negative 5 plus 20x minus 65. And then lastly, we will have negative 5 here. And the remainder is 0, which tells us that the original function equals to the product of these two zeros factors and x squared plus 4x minus 4. Now, x squared plus 4x minus 5 can be easily factored as x plus 5 and x minus 1. So with that, the original function can be written as x minus 2 minus 3i, that's the given one, x minus 2 plus 3i, that's the conjugate one, and then x plus 5, x minus 1. At this point, the original function is completely factorized into linear factors, and as you can tell, there are exactly 4 of them. Last bonus problem. For this rational function, we need to find any vertical and horizontal asymptotes. Rational functions have numerator and denominator functions. Both of them are polynomial functions. So for this rational function, the domain is determined by the zeros of the denominator function, because if we set x minus 4 equals to 0, then x equals to either positive 2 or x equals to negative 2. These two need to be excluded from the domain. Therefore, the domain of this function is x cannot be positive 2, x cannot be negative 2, because these are the values that will make the denominator 0. But for vertical asymptotes, these two vertical lines, x equals to 2 and x equals to negative 2, are the vertical asymptotes because they represent the two vertical lines that the function graph will try to approach infinitely but will never touch. So that's how you find the vertical asymptotes for a rational function, by finding the domain or by finding the zeros for the denominator function. Horizontal asymptote. To find the horizontal asymptote, we need to compare the degree of the numerator function and the denominator function. So we compare this one right here, that's our n, this one right here, that's our m. So there are only three rules. If n is smaller than m, then the horizontal asymptote is y equals to 0. If n equals to m, then the horizontal asymptote equals to the quotient between the two leading coefficients. And if n is bigger than m, then horizontal asymptote does not exist. In this case, both of the degrees are 2. Therefore, in our case, n does equal to m. Therefore, the horizontal asymptote equals to the quotient of the two leading coefficients, which is 4 over 1. So y equals to 4 over 1, which equals to 4. So y equals to 4 represent a horizontal line, and that is the horizontal asymptote for this rational function.